This is section 6.3, part E, geometric random variables. In a binomial setting, the number of trials n is fixed in advance, and the binomial random variable x counts the number of successes. The possible values of x are 0, 1, 2, all the way up to the number of trials. In other situations, the goal is to repeat a chance process until a success occurs. Roll a pair of dice until you get doubles. In basketball, attempt a three-point shot until you make one. Keep placing a $1 bet on the number 15 in roulette until you win. These are all examples of a geometric setting. Although the number of trials is not fixed in advance, the trials are independent and the probability of success remains constant. So when you have a geometric setting, you will have to check bits instead of bins. So you're still checking to see if it's binary, so there should be a clear success and failure. Each trial should be independent, but we're gonna have a T instead of N. So the goal is to count the number of trials until our first success occurs, instead of having a set number of trials when you start. The success or the probability rate of success should still be the same in each trial. In a geometric setting, if we define the random variable y to be the number of trials needed to get the first success, then y is called a geometric random variable. The probability distribution for y is a geometric distribution. The number of trials y that it takes to get a success in a geometric setting is a geometric random variable. The probability distribution of y is a geometric distribution with parameter p that the probability of success of any trial. The possible values for y are 1, 2, 3, and it continues on forever because there is no point where it has to stop. You will only stop when you reach a success. As with binomial random variables, it's important to be able to distinguish situations in which a geometric distribution does and does not apply. The random variable of interest in this game is y equals the number of guesses it takes to correctly match the birthday of one of your teacher's friends. Each guess is one trial, and the chance process. Let's check the conditions for the geometric setting. So we're going to start with B, or binary. It is a success if you guess correctly. It is a failure if you guess incorrectly. Now, each student's guess is independent. It is not influenced by the guess before them. So these are independent trials. We are counting the number of trials up to and including the first correct guess. So the T portion of this, the trials, is met. And the S, success, on each trial, the probability of correctly guessing the day of the week in which one of your teacher's friends is born is 1 out of 7. This is a geometric setting because y counts the number of trials to get the first success. It is a geometric random variable with a parameter of p equals 1 out of 7. What is the probability that the first student guesses correctly and wins the birthday game? The probability of this, probability of y equals 1, is 1 out of 7. That is also the class's chance of getting only one homework problem. For the class to have 2 homework problems, the first person had to have guessed incorrectly, and the second one must have guessed correctly. So the probability of y equals 2 would be 6 out of 7, because there's 6 out of 7 ways that they could guess wrong, and then times 1 out of 7, which would give us a probability of 0.1224. Same with 3. If they took 3 guesses, it'd be a failure, and then a success. So in general, the probability that the first correct guess comes on the kth trial, so the probability that y is equal to k, is going to be the probability of failure raised to the k minus 1 times the probability of success. So if the probability of success happened on the 5th trial, we would do 6 over 7 raised to the 4th power, because there was 4 failures, and then 1 success times 1 over 7. So if we summarize this, the probability that y is equal to k is going to equal the probability of failure raised to the k minus 1 times the probability of success. Let the random variable y be defined as the previous example said. So find the probability that the class receives 10 homework problems as a result of playing the birthday game. So find the probability. We would just do y is equal to 10. It would be failures the first 9 times. The probability of failure was 6 out of 7. Raise that to the 9th power times the probability of success. You were successful in that 10th trial. And that would give you 0.0357, or about a 3.5% chance that you will have 10 homework problems that night. Find the probability that y is less than 10 and interpret this value in context. To do this, you would have to find the probability of each y value that is less than 10. So you would find the probability of 1 problem, 2 problems, 3 problems, 4, all the way up to 7. So the probability there would be 1 problem would just be 1 out of 7. The probability there would be 2 problems would be 6/7 times 1/7. Probability there would be 3 would be 6/7 to the 2nd times 1/7, and you continue this on all the way up to the 9th trial, and that would give you 75%. So there's about a 75% chance the class will get less homework problems by playing the birthday game. Now, it's not always fun to do those by hand, so good news, your calculator can do this for you. To do a geometric probability, if you want to know exactly the value, you're going to do Geomet PDF to find y equals k, and you'll do Geomet CDF if you want to find the probability that y is less than or equal to k. To get to those values, you're going to hit second vars, and then you'll go down until you find either Geomet PDF or Geomet CDF. The table below shows part of the probability distribution of y. We can't show the entire distribution because the number of trials it takes to get to the first success can be an incredibly large number. So here is the table that we have. So if we're looking, this was for the birthday game. So the probability that there was 1, 2, so on and so forth. So if you need to find the mean or the expected value for a geometric random variable, you're just going to do 1 over the probability of success. This tells you on average how many trials you will have to do before you are successful. So in that birthday game example, our probability of success was 1 out of 7. So we would do 1 over 1 out of 7. When you have this, remember if you have a fraction over a fraction, you flip the second one and multiply. So that means we would expect that on average, someone would have to play the game or do 7 trials before they were successful. Below is a histogram of the probability distribution for the values of y from 1 to 26. Let's describe what we see. The shape is definitely heavily skewed to the right. This is characteristic of any geometric distribution. That's because the most likely value of geometric random variable is 1. You're most likely to get it correct. The highest probability is going to be that you get it correct on the first try. The probability of each successive value decreases by a factor of 1 minus the probability of success. The center, or the mean, is 1 over the probability of success, which we just said in this case would be 7 for the birthday game. And the standard deviation for this one is 6.48. So if the class played the birthday game many times, the number of homework problems that they received would differ from the average of 7 by about 6.5 questions. That could mean a lot more homework or a lot less homework. So let's check our understanding. Show that t is a geometric random variable. In this case, we're going to roll a fair 6-sided die, 2 fair 6-sided die until you get doubles. Let t be the number of rolls that it takes. To check to see if this is a geometric random variable, you are going to check bits instead of bins. So you're first going to check that it is binary. Success is that you roll doubles. Failure is that you do not roll doubles. They are independent because dice don't have memory. The first roll of the dice does not affect the second roll. This is a T, trials, because you are rolling until you get doubles. And the probability of success is 6 times out of 36 you will roll doubles, or 1 out of 6, since we could roll doubles with 1s, 2s, 3s, 4s, 5s, or 6s. So this is a geometric random variable. Because y counts the number of trials to the first success, it is a geometric random variable with a parameter of p equals 1/6. Now we need to find the probability of t equals 3, and interpret this result in context. So if the probability of success is 1 out of 6, the probability of failure is 5 out of 6. So if you want to do this by hand, if you are successful on the third try, that means you failed the first 2 times, but you were successful the third time. The other way you could do this is to do it on your calculator, and you would do Geomet PDF. And either way you set this up, you should get a result of 0.11574. There's about a 12% chance that you will get the first set of doubles on your third roll of the dice. In the game Monopoly, a player can get out of jail free by rolling doubles within 3 turns. Find the probability that this happens. So this is the probability that you do this and that your t value is less than or equal to 3. Again, you can do this by hand. You can find the probability that you do this on the first try, probability you do this on the second try, or the probability you do this on the third try, and you can find each of those probabilities by hand. This would just be 1 out of 6 plus 5, 6 times 1 out of 6, and this one would be 5, 6 squared because you failed twice, and then you were successful once. Or you can do Geomet CDF. The probability of success is 1 out of 6. You want to check for the third try, and this would give you a probability of 0.42, or about 42% chance that you will roll doubles within the first 3 tries. You will get the same answer whether you do it by hand